Hi. Today we're going to talk about bonds between atoms, and we're also going to talk about some of Pauling's rules. So the question becomes, what is it that defines the character of these interactions between this atom and this atom, or this atom and this atom? All of this goes back largely to a fellow, Linus Pauling, who received the Nobel Prize for his work in chemistry. So first thing I want to do is talk about the different types of bonds, and then talk about electronegativity, which brings up a Pauling's rule. And then the purpose of all of this is to allow students to distinguish between each type of bond based on some characteristics, to think about what mineral properties might be based on bond types, and then to classify the degree to which a bond is ionic versus covalent if a table of electronegativities is given plus a graph. So types of bonds. There are four types of bonds that we consider in Earth materials: ionic bonds, covalent bonds, metallic bonds, and residual bonds. There are two of these, van der Waals and hydrogen. Some people don't refer to these as bonds for reasons that are, I think, more historical in character, but I'm going to refer to them as bonds. An ionic bond is essentially an electron exchange. So it forms a moderately strong bond. And so the notion is that an atom like sodium might donate an electron to an element like chlorine. This would give chlorine a net negative charge. This would give sodium a net positive charge. And the electrostatic forces between the two would cause them to couple together to form an ionic bond. So here's the same thing. Here, sodium donates an electron and gets smaller. Chlorine takes up an electron, gets bigger, and it forms this ionic bond. Ionic bonds, these form salts that dissolve easily in polar solvents like water. And they tend to form crystals with very high symmetry, and that's because the cations tend to surround themselves pretty evenly with the number of anions. These have moderate hardness. The maximum hardness I found was 6 for magnesium fluoride. The density is moderate, up to 3 grams per cubic centimeter. A lot of rocks, granites, for example, are 2.75. Rocks from the mantle are 3.25 and higher. So 3 is kind of right in the middle. They tend to have high melting temperatures, and they're poor conductors of heat and electricity. Here's another example of an ionic bond. Magnesium oxide is fairly ionic. So if you look at this, how many valence electrons are there in magnesium, and how many valence electrons are there in oxygen? Magnesium is over here in column 2. Oxygen is over here in column 6A of the periodic table. And the answer is 2, and as a consequence, magnesium can donate 2 electrons. Oxygen has 6 valence electrons. It would like to have 8 in its outermost shell, so it can take up those 2 valence electrons. Covalent bonds refer to electron sharing. This usually involves nonmetallic elements. These are very stable, they're insoluble, and they have very high melting temperatures. And they're really bad conductors because all of the electrons are intimately involved in a bond. So they're good thermal and electrical insulators. Whenever you have a single elemental composition compound, so here Cl2, that is the most covalent bond that can form. Here chlorine, let's say this electron started out with this chlorine atom and this electron started out with this chlorine atom. They share these 2 electrons to fill up their outermost shells. And so the Cl2 atom makes a very, very strong bond. Diamond is a good example of a solid with very strong covalent bonds. There are 4 valence electrons in each carbon atom. It would like to have 8. So each carbon atom will share 1, 2, 3, 4 electrons with neighboring atoms to form a very, very stable compound. A metallic bond is sort of a strange one. The way I've heard this described is free electron sharing. So the notion is that there are positively charged atomic nuclei, and they have this sea of electrons that basically wash around among all of these ions. As you know, metals are highly conductive electrically. Also, they conduct heat very well. They tend to involve the transition metals. They all have very low ionization potentials. That means they don't hold on to their outer electrons very strongly. And as a consequence, the valence electrons migrate or roam around the mineral between the atoms. And this forms very soft and ductile materials. So here's some copper wire. It has been formed from some copper crystals. So which compound here would have the most covalent bond from the preceding discussion? And the answer is the carbon-carbon bond. So two of the same element that form a bond will have the strongest covalent bond, as long as it's a covalent bond. Copper-copper bonds here, that's a metallic bond. Sodium chloride, an ionic bond. H2O, it has some degree of covalency to it, but they're two different atoms, and so the degree to which they are covalent is less than in a carbon-carbon bond. And we'll come back to this later. Residual bonds are bonds that involve the attraction of partially charged atoms or molecules. And so the notion is that it's possible to create a polar atom or molecule that has a concentration of negative charges on one side and a concentration of positive charges on the other side. So here's an example of some diatomic molecule that has the electrons drawn over more towards this ion, less towards this ion. And that means that this ion has, on this side of the molecule, it's slightly negatively charged and it's slightly positively charged on this side. Well, this side of this molecule can line up with this side of this molecule with an attractive force that holds these two molecules together. There are a couple different kinds. Van der Waals bonds, also called London dispersion, it has to do with charge synchronization. So here's an atom. It's got some net positive charge, and it's got a bunch of electrons moving around it. And here's another atom with the same kind of situation. It's got a positive charge in the middle with these electrons moving around. Just by random chance, the electrons will tend to, at some point, bunch up on one side of an atom instead of the other. Now, when that happens, the atom develops a net very slight negative charge on one side and a very slight positive charge on the other. Well, the atom next to it can synchronize with it so that when this atom has a net negative charge on this side, this atom also has a net negative charge on its side. And the net positive charge on this side synchronizes with the net negative charge on this side to hold these two atoms together. Now, it's super weak. Like super weak bond, and it's characteristic of very, very soft minerals. So here's an example of van der Waals bonds in graphite. So graphite consists of these sheets of carbon atoms. The carbon atoms up here are held together with covalent bonds, so they're super, super strong. Graphite is super strong in that one sheet, and that's why we use graphite to make high performance materials. It's because of that strength along the sheet. But between the sheet, there's no strong bond that holds them together. Instead, the charge on this sheet is synchronized with the charge on this sheet and the charge on this sheet, so that when there's a slight negative charge towards the top of this sheet and a slight positive charge towards the bottom, there's also a slight negative charge towards the top of this sheet that connects with the slight positive charge on the bottom of this one to hold these two sheets together. Now, not very strong, right? That's why graphite is so weak. Those sheets are capable of sliding past each other very easily, and that's why we use pencils for writing. Hydrogen bonds, these occur because hydrogen has only one electron. So when hydrogen shares its single electron, in a strongly covalent bond, it exposes one side of the hydrogen nucleus. So this side of the molecule is slightly positively charged, just like this one is slightly positively charged for the two hydrogen atoms here. On the other side, this side of the oxygen atom has a bunch of electrons to it, so this side is very slightly negatively charged. And it's the slight positive charge on this side and the slight negative charge on this side that can attract each other and hold these two molecules together. It's a weaker bond than ionic or covalent bonds, but it's much, much stronger than van der Waals bonds. This occurs in minerals like serpentine. So here's the structure of serpentine: octahedral sheet, tetrahedral sheet. These are hydrogens sticking up from the octahedral sheet. And these hydrogens interact with the oxygens in the tetrahedral sheet to hold these two sheets together. So serpentine is pretty soft, not as soft as graphite. So based on hardness, which compound would you predict has a van der Waals bond? You kind of need to know your Mohs hardness scale, but it's talc. Quartz, diamond, K-feldspar, these are all very hard minerals, and they all have covalent bonds to them, strongly covalent bonds. So at this point, I think you should be able to, with some review, explain the different types of bonds and the materials that exhibit them, and then predict something about the bonds in the mineral based on the mineral's physical properties. Now, the last part of this lecture, I want to talk about electronegativity. So I've been talking about these bonds as covalent or ionic, but usually they are a mixture of bond types, at least if the two atoms are different. So the degree to which each type is covalent versus ionic is described in terms of a concept we refer to as electronegativity. So this is a little graph that shows different materials on here with a curve running through it. And this shows the percent covalent depending on what's called the electronegativity difference. Okay, what is electronegativity? Well, this is a description of how easy it is to gain or lose an electron. And this is where Linus Pauling came up with this definition. The electronegativity, chi, is a function of two different components. It's the first ionization potential. This is how difficult is it to kick an electron off of this atom. And the electron affinity, which is how easy is it to add an electron to an atom. And then there's a constant here. The constant is something that Pauling made up. And he did this so that all of the electronegativities would be normalized to a maximum electronegativity, which happens to correspond to fluorine, for a value of 4. Here's a table of the electronegativities on a periodic table, and you can see that as you move to the right across the periodic table, all of the electronegativities get higher and higher. And what does that mean? It means that as you come over to this side of the periodic table, not too surprisingly, because you know this from electron orbitals, it's very easy to add an electron, and it's very hard to remove an electron. Whereas on this side of the table, it's very easy to remove an electron, and it's not so easy to add one. The degree to which a bond is covalent versus ionic is given by the electronegativity difference. So we look at chi for one atom and chi for the other atom. We take the difference and we look at the value. And the larger the value, the more ionic the bond is. So the maximum value of chi on our table is 4 for fluorine, and the minimum value is 0.7 for cesium. The difference between them is 3.3. So the most ionic bond is like 3 to 3.5. The most covalent bonds correspond with monoatomic compounds. So what do I mean by that? A molecule that's made up of only one type of atom, like oxygen. Oxygen, the electronegativities of the two atoms are identical, so the electronegativity difference is 0, and those are purely covalent. So here's an example. If we look at magnesium, 1.31, oxygen, 3.44, delta, 2.13, this is a fairly ionic bond. If we look over here, 2.13 is in here somewhere, And so the degree to which it is ionic is very high. Silicon, 1.8, oxygen, 3.5, a little bit of a difference here depending on what table you look up. Delta is 1.7, we go to 1.7. We're sitting up here, it's about 50% ionic, 50% covalent. Then if we look at arsenic sulfide, arsenic is 2, sulfur is 2.5, the difference is 0.5. If we look at 0.5, those kinds of bonds are almost completely covalent. So the sulfosalts have a lot of covalent bonds to them. There are 4 categories of bonding. If the 2 elements have low but similar electronegativities, they tend to form metallic crystals. If they have very high but similar chi, they form covalent crystals. If they're extremely different, they form ionic crystals, and that's really a lot of oxides and salts and silicates tend to be pretty ionic, although they can also be quite covalent. And then there's all sorts of intermediates, the sulfides, the arsenides, some oxides, and so on. So here's a test. Lead has an electronegativity of 2.2. Sulfur has an electronegativity of 2.3. What type of bond do you think galena is likely to exhibit? Mostly covalent, mostly ionic, something in between? And the answer is mostly covalent. The electronegativity difference is only 0.1. We come to 0.1, that's essentially 100% covalent. So at this point, I hope that you're able to explain the different types of bonds and how those affect a mineral's physical properties, and then to predict the type of bond from electronegativity. If you have a table of electronegativity values and you have a graph that correlates electronegativity difference with bond type. Thanks.